Hello, class. Just an FYI, my internet is not working too well today, so um, hopefully you can follow um, the lesson. I'll wait another minute or so. This is actually a really tiring day for me because normally I teach for about half of the class period and then we just kind of hang out in the Zoom room for the second half. But today it's like teaching for the full 4 hours. Okay, I'm going to go ahead and get started. A couple of announcements. Today's class ends at 11:25, and then you have a 5-minute passing period, and your 7th period class will begin at 11:30. So I wanted to make sure that everyone understands that. The other thing I wanted to say is that we will have no Zoom room today because of the shortened class period, but you still need to submit the attendance form. So please submit the attendance form with your student ID so that I don't mark you as absent, because I won't see you in the Zoom room. So I will have no clue who's watching unless you submit the attendance form. Okay? Today's lesson, you're not going to know how to do today's quiz at the end of this lesson. So don't start the quiz until after Friday's lesson, okay? So there's only one quiz that's assigned this week, all right? So let's go ahead and get started. Today, we are going to talk about something called angular momentum, which is denoted by L. So we have been talking in the class about the analogy between linear motion and angular motion. And so just like there's a linear momentum, there is also an angular momentum, which is analogous to linear momentum, but for rotations. So it's kind of hard to understand what it is intuitively. I would say roughly angular momentum quantifies the amount of spinning. Okay? It quantifies how much spinning is going on. All right? And so there are kind of two types of angular momentum. So if we think about something spinning, if I think about this calculator is going around in a circle, there's two ways that it can spin. It can spin like this, where it's as a whole, it's moving around a central point, or it can spin in place. All right. And so those are two. They're both angular momentum, but they're different types of angular, or they have different names just to help us understand. And so there's something called an orbital angular momentum. Orbital angular momentum is motion of the object as a whole around a central point. Okay. So that's what's called orbital angular momentum. So the Earth is rotating about the sun, which is its central point. So that would be orbital angular momentum. Okay. And then you also have something called spin angular momentum. Which is rotation about an axis. Okay, so when I think about spin angular momentum, that is something going like this. See how it's just spinning in place? Okay, and orbital angular momentum is going as a whole in a circle. Okay, so you can have both. So for example, the Earth is spinning while it orbits. It's kind of going around like this, right? Okay, so you can have both. You might have learned in your chemistry class about spin angular momentum. The spin angular momentum, remember when you were talking about electrons, how they could be spin up or spin down? They could be plus 1/2 or minus 1/2. That's the spin angular momentum of the electron. And then electrons also have orbital angular momentum. So you might have remembered the SPDF. Those are letters that stand for certain orbital angular momentum of the electron as it goes around the nucleus. So you've actually heard about these two things before in chemistry. Type it into the chat if you remember. If you don't, not if you still remember it exactly, but if that rings a bell. If that rings a bell for you, SPDF and spin up, spin down, plus 1/2, minus 1/2 from chemistry. I'm curious if anyone remembers that. So the first thing I want to talk about is orbital angular momentum. So orbital angular momentum, what we want to think about is an object moving in a circle. And the speed of that object around its circle is v. The radius of that is r. And the mass of the object is m. So the orbital angular momentum of this thing is the orbital angular momentum is m times v times r. So that is the definition of orbital angular momentum. Okay. So how do you have a lot of spinning, a lot of orbital spinning? You're going in a big circle and you're going really fast. All right. Based on this, we can calculate, or we can determine the units of angular momentum. So angular momentum is a mass times a speed times a radius, which is a distance. So we have a mass, which is measured in kilograms, speed, which is meters per second, and then a distance, which is r. That's another factor of meters. So we have kilogram meters squared per second. Okay. So what I want to talk about and we're going to come back to spin angular momentum, okay? Why is angular momentum useful? Why is angular momentum a useful thing to talk about? Well, it turns out that if a system has no torque acting on it, and that's an important point, okay? If it has no torque acting on it, angular momentum is conserved. Okay? So it's a conserved quantity, just like energy. Energy is conserved. Just like linear momentum. Linear momentum is conserved in collisions. So, and things being conserved makes it easier to solve problems. So that's why makes it easier to predict what's going to happen. So that is why angular momentum is useful. So that means that the angular momentum is a constant. That's one way of thinking about it. Another way of thinking about it is the initial angular momentum is equal to the final angular momentum. Okay? And when I say the angular momentum, I mean the total angular momentum. Okay? Which would be the spin angular momentum plus the orbital angular momentum for each of the particular objects. So for example, in the solar system, each planet has a spin orbital angular momentum and a both spin and orbital angular momenta. Okay, so let's do an example. Let's suppose you have a tetherball. I don't know if kids still play tetherball, but when I was a kid, I used to play tetherball. And I was always horrible at it because I was so short. Still am short, so I still probably would be horrible at tetherball. But the other kids used to just hit the ball so that it would go in a circle above my head, and I was just like, yeah, I can't hit the tetherball, and I would just get beat instantly. So anyways, let's suppose we had a side view of a tetherball game. Okay, so you have a pole. Here's the tetherball pole. And here's the rope. Okay, and then there's the tetherball. And it's going around in a circle like this. Around the pole. Okay. And so let's say it's moving around its circle with a speed of 3 meters per second. Okay? And furthermore, the radius of that circle that it's moving in is 2 meters. Okay? All right. Now, what happens in a tetherball game is after some time passes, is the tetherball winds up around the pole. So the tetherball is going to be like, and because it's winding up, the string is now getting shorter, and so the radius of the circle is now smaller. Okay. So now the radius of the circle is only 0.35 meters. And so what we would like to calculate is what is the final speed of the tetherball after it has wound up. Okay? And so we're going to use angular momentum conservation. So why is angular momentum conserved? Well, it's because the net torque is 0. The torque by the way, we could talk about why does no torque have to be acting on a system? Well, torque causes something to spin faster or slower, right? That's what torques do. It's a twisting force. So torque changes the amount of spinning. So in order for angular momentum to be conserved, you have to have no torque. And this rope, clearly the rope, all it does is it pulls in towards the center. It doesn't make the ball go faster or slower around its circle, okay? So since the perpendicular component of that tension is 0. Remember, torque is F perp times R. All right? So that means that the initial angular momentum is equal to the final angular momentum. So if I write that as an equation, it means mvr equals mvr. Where on the left-hand side, I have the initial values of the mass and the radius. And on the right-hand side, I have the final values of the mass and the radius. Okay? It's the same tether ball, so its mass is the same before and after. And because all the terms have mass, it cancels out. So it was not necessary for me to give you the mass of the tether ball. So now we simply plug in numbers. Well, the initial speed is 3 meters per second. The initial radius of the circle is 2 meters. The initial, the final velocity is unknown, so I'll leave it as a variable. And the final radius is 0.35. Okay. So we can solve for the final speed. Let me use my calculator. And we get that the final speed is 17.1 meters per second. Okay, so we can see that as it wound up, the speed increased from 3 meters per second to 17.1 meters per second. So generally what angular momentum conservation says is that kind of like things speed up as they wind up. That's one of the things that angular momentum says. Okay? Angular momentum has a sign as well. Counterclockwise rotation implies L is positive. Clockwise rotation implies L is negative. Okay? One thing I think is really neat that I wanted to talk about is the solar system. Let's talk about the angular momentum of the solar system. Okay? So I'm going to draw the solar system not to scale at all. Okay? This is not to scale. But we have the sun. We have Mercury. We have Venus. We have Earth. We have Mars. We have Jupiter. We have Saturn. We have Uranus. And we have Neptune. Okay? And again, this is not to scale. It turns out that all of the planets are orbiting around the sun in the same sense. They all have positive orbital angular momentum. Okay? They all have positive orbital angular momentum. They're all going counterclockwise. Did you know that? I bet you didn't know that. So the orbital angular momenta are all positive. Furthermore, the spin angular momentum of almost all the planets is also positive. So the sun is spinning counterclockwise about its axis. The spin of Mercury is counterclockwise. The spin of the Earth is counterclockwise. The spin of Mars is counterclockwise. The spin of Jupiter is counterclockwise. Saturn, counterclockwise. Uranus, counterclockwise. Neptune is counterclockwise. Okay? Venus is clockwise. We'll talk about why that is in a second. But I find that fascinating. They all have the same spin angular momentum, and it's consistent with the orbital angular momentum. Okay? Then we can look at the moons. If we look at the Earth's moon, it orbits counterclockwise. Furthermore, the Earth's moon has a spin angular momentum that's counterclockwise. Mars has two moons named Deimos and Phobos, and guess what? They both orbit counterclockwise. And guess what? They both spin counterclockwise. Jupiter's moons, same thing. Saturn's moons, same thing. Uranus's moons, same thing. Neptune's moons, same thing. So almost everything in the solar system goes and spins counterclockwise. Okay? So why? Why is that? We believe this is because the entire solar system was formed from a primordial cloud of dust and gas. Okay? And that cloud, that original cloud of dust and gas, was spinning counterclockwise. So if you think about it, so what happened is then gravity started to act on that cloud, and it started to shrink the cloud down, and then the sun formed out of that cloud. It all gravitated. But if you think about it, if you start out with something that's rotating counterclockwise, it's very hard to get things to orbit in the reverse sense. Okay? So we think it all came from the same cloud, and that's why everything is spinning the same way. And there are other pieces of evidence for that as well. I mean, we can look out through telescopes and we can see other solar systems about other stars that are not fully formed yet, but are in the process of being formed. And we can see that that's what's happening. It's turning into a star with planets, and everything's rotating the same way. We can also look at the composition, similarities in the composition between planets to tell that it all came from the same cloud with the same composition. So anyways, I think that's really neat. Everything is spinning the same way with the exception of a few things. Now, why is Venus spinning the opposite direction? We believe that in the early solar system had a lot more debris in it. Now that the solar system has aged, all that debris has fallen on top of the various planets. Okay? But in the early solar system, there was a lot more debris, and that debris was falling onto planets. It was gravitating towards planets and getting pulled onto them. And so impacts, like asteroid strikes, that kind of thing, were a lot more common in the early solar system. And so we believe that Venus got smacked really hard by something else that was probably about the same size. So there were two masses that were about half of the current day Venus mass, and they hit each other, and that impact was so violent that it reversed the spin of Venus. Okay. So yeah. Another thing I wanted to talk about is I wanted to just give you the formula for spin angular momentum. So orbital angular momentum is mvr. Spin angular momentum is the inertia of the spinning object times omega. Okay. And then your total angular momentum is just the sum of the orbital plus the spin angular momentum. Okay? Now, you can actually have, because the total amount stays constant in the absence of torque, you can have transfer from orbital angular momentum to spin angular momentum. Okay? So they can go, you can transfer. So if you lose orbital momentum, you gain spin angular momentum, etc. One thing that's really interesting is, have you ever noticed that the same face of the moon is always pointed towards the Earth? Okay, so it's not necessarily true that a moon has to orbit with the same period as, if we think about it, you could have something orbit like this, where it's not spinning at all. But what the moon is doing is as it's orbiting, it's also spinning so that the same side of the moon is always facing us. Okay? And it turns out that phenomenon is called tidal locking. And almost every moon in the solar system is tidally locked to its planet. So that is not a feature that is just for the moon. Okay? It is for basically all of the moons in the solar system. Okay? And that happens via a spin-orbit interaction that transfers angular momentum from spin to orbital until the spin rate is the same as the orbital period. All right? So that's kind of cool. The last thing I wanted to talk about is the analogy between linear and rotational motion. Okay, so you might recall that linear momentum is P equals mv. Most valuable physicist. Angular momentum, at least the spin form of angular momentum, is analogous to linear momentum. So what is analogous to mass? Inertia is analogous to mass. What is analogous to linear speed? Angular speed. So the formula is exactly the same. All right, so I think that's kind of interesting. All right, class, that's my lesson. Remember, don't start the quiz yet because you don't know all this stuff. And I will see you on Thursday. Remember to submit your attendance form. Okay?